Happy April 3rd and happy birthday to my friends Christine, Joan, Mary Frances, Ryan, and Amber. I hope you have a happy birthday. I know these are unusual times and it's kind of hard to celebrate in maybe the normal way that you usually celebrate your birthday, but I hope it's a wonderful day for you. Silly fact for today, a cow crossed with a buffalo is called a beefalo. Did not know that. All right, today I got a request to talk about the first derivative test. This is a calculus concept. One of my very favorite things to teach is calculus. I like teaching all high school math, but I especially love calculus. And I used to get paid to do this, and it was awesome. And I had an audience, it was wonderful. And now I'm gonna do it, not getting paid, but that's okay. It's still gonna be fun. All right, first derivative test. I'm going to assume that you know what a derivative is. I'm going to assume that you know how to find the derivative of a function. But let's talk about the derivative. You know that the derivative tells you the rate of change of a function. Basically, it is the slope of the tangent line of a function. The instantaneous rate of change of your function at a specific moment in time. All right, let's look at a function that we've probably seen a lot recently. We're gonna look at an exponential function. And in this exponential function, the x-axis is our time. For example, February, March, all the days in March until we get to April, and so on. And the y-axis is going to represent the number of COVID-19 cases. Kind of a scary thing that's going on. As you can see on this graph, as we go from left to right, from let's say day 1 down to whatever day this is here, you can see that the y values, the number of cases, whatever they are, I'm not going to actually put values here, but you can see that they are increasing, that these y values are getting larger and larger and larger. And when a graph gets larger, the y values get larger as you go from left to right. So as I go from left to right and I examine this graph, my y values are getting larger and larger. We say that that graph is increasing. Well, how does this tie into derivatives? Well, a derivative is the slope of the tangent line. So let's look at some tangent lines here for just a minute. And we're going to see how the tangent line or the derivative might be able to help us figure out what a function is doing just by looking at the derivative, not even having the graph. But we have both here, so or we have the graph here. So let's say I took a point right here and I examined the tangent line here. And a tangent, remember, is a line that just touches that graph at one point in that interval, in that particular area, that general vicinity. If you look at that line, that green line there, we would say that that has a positive slope. It's not very steep. It would probably be kind of a low slope number. And then down here, if we look, let me do this one in a different color just to emphasize. Over, let's say this was today, somewhere April 3rd, and we were to examine the tangent line here. We want to draw a line that just touches at that point. We would see that the steepness of this line is larger than this one. This is much more steep than this line. It still has a positive slope, but it's larger. So the derivative is going to help us tell when a graph is increasing or decreasing. If your slope, your tangent, your derivative is positive, it tells you that your graph is increasing. If, let's look at something else, another type of function. Let's say that I had this function. And let's look at this one and just imagine the tangent lines for just a minute. So here's some tangent lines. These are pretty steep tangent lines. All of these tangent lines have a positive slope. That means their derivatives are positive. Now look at the original function, the black curve. What is the black function doing where the slopes were positive? these slopes are all positive over here. All of these slopes are positive. Then ignore the green for just a minute. Look at the black. From left to right, if I trace this, what's happening to my y values? My y values were negative here, but as I go to the right and I slide my pencil on, my y values are now into the positive region. They're getting bigger and bigger. My y values are getting larger. So we say that this graph is increasing on this interval until about right here, something unusual happens. If I were to draw a tangent line right there, the tangent line would actually be a horizontal line. And you remember that the slope of a horizontal line is 0. At that point, it leveled off. Now, to the right of that, let's see if it goes up or down. Well, going to the right, if you look at the tangent lines here, look what's happening. Those lines are going down from left to right. All of those tangent lines are going down. They have a negative slope. And if you look at the graph, sure enough, the graph, all those y values are going back down. It reached kind of a little relative maximum here, which we'll talk about later. Reached a relative maximum, and then the y values got smaller. So we say that in this interval of the graph, it is decreasing. I'm going to abbreviate that until right here, we see that levels off again. The tangent line there, the derivative there is 0. It has a horizontal tangent line. And then to the right, the tangent lines have a positive slope. And you look at the graph, the y values are getting larger and larger. We say that it increases there. So the derivative is going to be able to tell us something about the original function. Where the derivative, the slope of the tangent line is positive, it's going to tell you that your original function increases on that interval. Where the derivative is negative, whatever that interval is, will tell you where your function is decreasing. And again, where the derivative is positive, it will tell you where your function is increasing. Where your derivative is 0, it gives you something called a critical point. Critical points can be places where it changes from increasing or decreasing, but not necessarily. Let me show you a critical point where it is not where a graph changes from increasing and decreasing, but it's still a critical point. It's still where the slope of the tangent line is 0, or where the derivative is 0. If you look right here, this graph is increasing. All of these slopes of the tangent lines would be positive until about right here. That would have a horizontal tangent line. We would say that the derivative there, the slope of that tangent line is 0. That levels off. And then look what happens on the right of that. If we continue along from left to right, you'll see that these slopes are positive again. So the slopes to the left of that critical point, I'm going to call that critical point A. To the left, the slopes were positive and it leveled off. And then to the right, the slopes were also positive. So we would say that this graph increases on both sides of that critical point. So just another little review. I think that this would probably be in the section before this. Your critical points are where your derivative is 0, which tells you where you have horizontal tangent lines. Or critical points can also be where the derivative is undefined. And that could be because your graph comes to a cusp and there's not just one tangent line. It's like an infinite number of tangent lines there. You can have a cusp. Could be kind of flared, or it could be a sharp point, like an absolute value graph has that sharp V shape. It could also be where you have an asymptote, where the original function is undefined. And those are important things to know about your function. So those critical points are where the derivative is 0 and where the derivative is undefined. So keep that in mind. All right, we're going to jump in now with how to use the first derivative, the slope of the tangent line, to help us determine where a function, the original function, is increasing or decreasing. And just to kind of condense all this and summarize, where your derivative is positive, is going to tell you where your original function increases. Where your derivative is negative is going to tell you where your original function decreases. It doesn't necessarily mean that it's going to be above or below the y-axis. It doesn't mean that. It just means that your graph is increasing where the derivative is positive, and it's going to be decreasing where your derivative is negative. Where your derivative is 0 is where your graph levels off, and where it levels off could be a little maximum, a relative maximum or minimum point, or it could be just where it levels off, and then the graph still continues to do what it was doing before, but it could be where it changes from increasing to decreasing. All right, let's look at an example and see if this helps. I'm not going to do any real-world applications yet, but if you want a real-world application like a word problem, we'll do that. Right now, we're just going to take a function and we're going to answer some questions about it, see what we can determine about this function using calculus. All right, here's our function. It's a cubic function, x cubed minus 3/2 x squared. And let's say the directions ask us to tell where is f of x increasing and decreasing. Basically, on what intervals is the function increasing and decreasing? Okay, here we go. To tell where the function's increasing or decreasing, we need to know where its derivative is positive and where its derivative is negative. To do that, let's find the derivative. So we're going to take the derivative of this function. I'm going to use my power rule. The derivative of x cubed is, as you know, 3x squared. If you don't know that, let me know and we'll do a lesson on the power rule. All right, the derivative of 3/2 x squared is 3x. Once you find your derivative, you need to find the critical points. To find the critical points, you see where your derivative is undefined, and you also see where the derivative is 0. I'm going to call them, they're our little friends, the CPs. That's their nickname, critical points. So first of all, you want to set the derivative equal to 0. And then we also want to see if the derivative is undefined anywhere. F prime of x, the derivative is undefined. Where? F of x is undefined where? Let's see where it's equal to 0, and let's see if it's undefined anywhere. To see where it's equal to 0, we're going to set this equation equal to 0. This is a quadratic. So you remember from algebra how to solve quadratics. Lots of different methods. You could complete the square, you could use quadratic formula, or in this case, this is a nice one, you can factor it. So let's factor it. Make sure it's set equal to 0, which it is, and we're going to factor out the greatest common factor. These two terms have a 3x in common. Those are both factors, so I'm going to factor out a 3x. When I factor out a 3x, that leaves x minus 1. So I have two factors here. I'm going to set those equal to 0 and solve for my two critical points. So when I do that, when I set 3x equal to 0 and solve it, I get x equals 0. And when I set x minus 1 equal to 0, I get my second critical value, which is x equal 1. So let me write those up here. Those are my little CPs. So I set my factors equal to 0. I'll just write that up here. We're finding our CPs, our critical points. 3x equal to 0. That gives us x equals 0. Set the other one, and I get x equal 1. Those are my critical points. Those are the places where the graph is going to level off. Okay, that's where you have a horizontal tangent line. This is where the derivative was equal to 0. Those are horizontal tangent lines, just reiterating that. Horizontal tangents. Okay, the other place you might have a critical point is where the derivative is undefined. And right here was our derivative, 3x squared minus 3x. That is a normal polynomial function. It is defined everywhere. We know that because every number for x from negative infinity to positive infinity, you can square, you can multiply it by 3, You can subtract 3 times that number. There's no place that this is undefined. Normally, where you are going to have problems or where your derivative might be undefined is when you end up with a quotient and a denominator, and you know that the denominator cannot equal 0. You cannot divide by 0. It's undefined. We could talk about that another time. So those are the things that you need to worry about. In this case, this derivative, 3x squared minus 3x, is defined everywhere. There's no values of x that you can't plug in here. You can plug in any number for x that you want, and it will give you an answer. So it is defined for every value of x. Okay, so all we have are these 2 critical numbers. And remember, those are the places where the graph levels off. And those are the places that I need to look at carefully. I need to look at the left of those critical values. I need to look in between the 2 critical numbers to see what's going on with the tangent lines. And I need to look at the right of my critical numbers. So once you find your critical points, all of them, we're going to do something called a sign analysis. And a sign analysis is where you see where the derivative, and if you remember, our derivative was 3x squared minus 3x, which we factored into 3x times x minus 1. Those are the same, those are equivalent representations of the derivative. I want to know, where is my derivative positive? That tells me where the slopes of the tangent lines are positive. I want to know where my derivative is negative. That'll tell me where the slopes are negative, which means my function's going to decrease there. So I'm going to analyze the derivative. I'm going to take my critical points and put them on a number line, and I'm going to evaluate the sign, positive or negative, of the values in my derivative. So this is an analysis of my derivative. I know that my derivative was equal to 0 at these 2 critical values, at 0 and 1. So let's just imagine this little number line going from negative infinity to positive infinity. Okay, this is just a normal number line. It is going to represent the value, the sign, positive, negative, or 0, of my derivative. My derivative is equal to 0 at x equals 0 and at x equal 1. So at 0, my derivative was equal to 0, and at x equal 1, my derivative was equal to 0. So I'm going to put those zeros up there to remind me the derivative was 0 at 0 and 1. These 2 critical numbers have divided my number line into 3 sections: to the left of 0, in between 0 and 1, and to the right of 1. And I want to analyze the sign of the derivative in those 3 sections. To analyze the sign, I pick a test point in each section. Starting with this first section, I'm going to pick any number I want from that's smaller than 0, any number. I could pick negative 1,000,000 if I want to. And let me show you how I evaluate it. Okay, remember, I'm evaluating the derivative, and I'm going to use the factored form of the derivative. Here's my derivative. That was the derivative of the function. If I pick negative 1,000,000, 3 times negative 1,000,000 is a negative number. All I'm interested in is the sign. I'm not interested in the actual number, just whether it's positive, negative, or 0. So I stick negative 1,000,000 in, I get negative. Times, I'm going to put negative 1,000,000 in here. What's negative 1,000,000 minus 1? Is it negative or positive? Well, negative 1,000,000 minus 1 is negative. If I multiply a negative times a negative, that gives me a positive. That tells me that the sign of the derivative of any point over here, when I plug it into the derivative, any point to the left of 0 is going to give me a positive for my derivative. Okay? I'm going to pick a number in between 0 and 1 and do a sign analysis. Okay, I'm going to pick the easiest one, I guess, for me to work with is 1/2. I'm going to plug it into the derivative. Here's my derivative. I'm trying to write small. Sorry, I hope this isn't too small. I'm going to plug a 1/2 in here. 3 times a 1/2 is positive. That's all I'm interested in, is positive and negative. A 1/2 minus 1 is negative. 1/2 minus something larger than 1/2 is going to be negative. A positive times a negative is negative. That tells me the sign of all the numbers in between these two critical numbers is going to be negative. Okay, to the right of 1. Again, I'm evaluating the derivative, and I'm going to use the factored form. It's easiest. I can pick any number I want. Let's just pick a normal number this time. Let's try 2. 3 times 2 is positive. 2 minus 1 is positive. A positive times a positive is positive. That tells me that every number, and you can try and pick some other numbers if you want, if you just want to confirm it. Oh, we have a guest. Let me see. Come in. Hello. You want to learn some calculus? Okay, come here. All right. Moon Pie says hello. She wants to learn some calculus. Okay, there you go. All right. So we now have our signs for our first derivative. We can see that the first derivative is positive from, on this number line, this goes forever and ever and ever to negative infinity. So our derivative is positive from negative infinity until I get to 0. The first derivative is negative in between 0 and 1. And then my first derivative is positive from 1 to, this goes all the way out to positive infinity here. Now, how do I write this as an answer to my question? If you remember, the question was, where is your function increasing and decreasing? Well, let me show you how to write that. Looking at my sign analysis. Oops, I should have left my little infinity up there. All right. I'm going to list the intervals where my function is increasing, and I'm also going to list where my function is decreasing. All right. It's increasing where the derivative is positive. So it's increasing on this interval and it's increasing on this interval. To list this interval, you start on the very left side and you end it where that interval ends on the right of that interval. So this interval starts at negative infinity. And if you remember the use of the parentheses and the brackets, use parentheses when the number is not included. And you can never equal infinity, so you always use a parentheses, whether it's positive or negative infinity. So it starts increasing from negative infinity until it reaches this critical point. At that critical point, it's not increasing or decreasing, it's leveled off. So 0 is not included. So it increases from negative infinity to 0. In between 0 and 1, the derivative was negative. That tells you where your graph is decreasing. So between 0 and 1, it's decreasing. And then from 1 all the way to infinity, the derivative was positive. So that tells me that my original function is increasing from 1 to infinity. So it's increasing from negative infinity to 0, union with the interval from 1 to infinity. That's where the function is increasing. It's decreasing from 0 to 1. So just to kind of show you what that would mean on the graph, now we don't have any actual y values for my function. I could get some y values. It would be very easy. But just to kind of give you an idea of what's going on, to put this all together, and then we're going to end this video and I'll see what else I need to cover for a second one. But if you just imagine, here's the x-axis. The y values I don't know, so I'm not going to put the y-axis on here as an exact y-axis because I don't want you to get hung up on where the y-axis is. But let's say here's 0 and here's 1 on the x-axis. If my graph is increasing until it gets to 0, that would mean that the graph would be increasing until it gets to 0, then it levels off. Between 0 and 1, the graph would be decreasing, and I don't know if it's going to go above or below the x-axis. I have no idea, but I know it's decreasing until it levels off, and then it increases again after that. And it levels off at 0, and it levels off at 1 because that's where the derivative was equal to 0. That's where it would have a horizontal tangent line. Okay, and if you remember, the original function was a cubic function, and cubes usually have this kind of shape. And so things are kind of aligning up with my past knowledge and my new knowledge. So using the first derivative helps you find out where a function is increasing and decreasing. It helps you get your critical points. and it's going to lead to some other kind of cool information as well. But that's the first derivative test in a nutshell. Hope that helps.